Hi, this is Mike, and today we're going to do another validation example with Inventor Nastran. Um, Let me move the sheet over here, and today we're going to do a rectangular plate with three edges simply supported, and we're going to apply uniform pressure. Comes from Rourke's Formulas for Stress and Strain, 5th edition, 1975, page 389, table 26, case 2A. It's a rectangular plate with three edges simply supported and a uniform pressure. That pressure will be 50 psi. The dimensions are 10 inch by 5 inch for the plate, and we will specify that it is a quarter inch thick. Again, the pressure 50 psi, thickness 0.25. Material properties that we will enter is 30E6 for our modulus and 0.3 for Poisson's ratio. Our target today is to get towards the 15,772 psi result. So what I've done in Inventor, you can see I'm using Inventor Professional 2022. I've sketched my rectangle already, and it should be a 10 inch by 5 inch, and we can just measure that. So there's one of the edges 10 inch, and there's the other inch 5, or other edge 5 inch. And so again, I just created that rectangle. And then what I did was created a patch so that I have a planar surface within that rectangle. So that is enough for me to be able to have the plate or shell elements or generate plate or shell elements within the Nastran. Now, in the prior validation, this is the validation number 5. In validation number 4, I also showed how you could end up with plate or shell geometry from a solid. So if you're interested in how to do that, I would reference you to that particular presentation. Maybe we'll show it again here in the future. In short, basically, if I had this as a three-dimensional object, when I take it into Nastran, Nastran has the tools to collapse it down to its mid-surface. While I won't demo it, we'll show it real quickly when we get into Nastran. But let's go ahead and get into the Nastran environment. So I will select the Environments tab, and Autodesk Inventor Nastran is what I want to utilize. Now, I've mentioned it again in the prior validation that I did, but since I don't have any solid geometry, it does not create the idealization with the solid and solid elements. So we need to go ahead and select it. We are going to define an idealization. So I'll click idealizations, and we are going to tell it that what we want to have is shell elements. And as soon as I select shell elements, then we can define what our thickness is. And the thickness of these elements will be 0.25 inch. And we are going to select the material. Now, when I select the material here, again, all we really need are the modulus of 30E6, and our Poisson's ratio will be 0.3. We could select something out of the library, but since we don't have gravity, or any acceleration load in this model. These are really the only properties that we need, so it's just as easy to type them in kind of quickly and have that completed. So there's our material, and we can choose what sort of elements we have. We can either choose from quads or triangles. I'm going to go ahead and leave it at quadrilaterals. For this demonstration, we'll say OK. And that should define everything. If you want to check anything, it goes into the browser here, so we can double click on our material, make sure our material properties are set right. We can double click on the shell idealization, make sure that we see the thickness there. Everything looks good with that. If you want to change the mesh color, you can do that right there. We're going to leave it as is. And so the next thing I'm going to do is just go ahead and generate my mesh. So we can go into mesh settings here. And we could generate the mesh with what it has there. I'm going to make it half-inch size element, so 0.5 on the element size. We don't need to run it as a parabolic. We can use a linear element order for this model. It should work just fine. Of course, if our results are kind of far off, we can certainly decrease the mesh size to increase our accuracy. It's one of the things that we can do to increase our accuracy, but I think this should be fine. So we'll generate the mesh, and there we go. So we have that. And next we'll do, or what remains to be done, are the constraints and the loads. So let's go in the constraints first of all. And I'm going to go ahead and first say free. The description is for the model to be simply supported on 3 of the 4 edges. So the 2 long edges are going to get the same constraints. So let's go ahead and select that long edge there, and then we'll select this long edge over here, and you can see the 2 edges are selected. Now, because the pressure is going to be to this whole face pushing down, we need to constrain, the model from moving in to space. My pressure will end up in the y direction, so we're going to constrain ty, and then the direction that we want to constrain is the other normal direction to that edge. So in my case, given how I constructed this model, that would be the x. So I'm going to constrain tx on those long edges as well. So pay a little bit of attention if you are recreating this model for yourself. What is the orientation of your model? So given how my model is oriented in the XZ plane, again, I'm going to constrain the direction that is opposing the pressure, in my case, the Y direction, and then the other normal direction, which again, in this case is X. So we'll do that, and maybe we'll name this one. So we'll call it long edge and say, okay, there are my constraints. And then we need the short edge constraint, so just selecting that short edge. And again, maybe we'll assign it a name, short edge. The name, completely up to you whether you want to add the names there for your constraints or not. Whenever I have a lot of constraints to apply to a model or a lot of different types of loads, then I like to start adding names to them. So that way, when they are added to the model tree, if I need to edit a particular constraint or load, it's easy for me to find it and see what it is, differentiate it from any of the other loads or constraints that I have applied on the model. So let's do the same thing here. We'll do free first, and we are going to constrain ty, and then you can see the orthogonal direction is to z, so we'll constrain ty and tz on that edge, and there we go. So again, that 4th edge we're going to leave free as per the problem description. The other thing we need to do is loads, which in this case will be a pressure. So let's select the pressure. Selecting our entities, we're going to select that face, and it will be a 50 psi. We can click the little preview button here. We can see there's our pressure. If I want it to be in the opposite direction, which I do, let me go ahead and make that a 50. And we can increase the density if we'd like. Again, increasing the density is not going to impact our results. It's just for display purposes, so we can see what those loads are, and you can adjust the size of them, etc. So given that I selected that face, of course, regardless of what the density of my arrows, display arrows are, that pressure is applied to that whole entire face. So I don't have to worry about it. Again, the density is just for visualization purposes. And technically, we could do the same thing with the constraints as well if you wanted to add more constraints along those edges. I didn't name the load. Let's edit that just so you can see. We'll call that pressure on face. There we go. There you go. So that way, as I was saying, if you have a lot of loads, a lot of different constraints, then you can, when you give them a name, you can see them quickly in the model tree and be able to edit them quickly. I think at that point we have everything defined for our analysis that we need to. Let's go ahead and run that model. This is about 200 elements. I think I saw something like 230 nodes, so it should run right quick for us. And when we come into the results, there we go. So it's on a shell von Mises by default. What we want, well, for my particular model, it's either going to be a shell X or a shell Y, depending on what is my local X and what is my local Y. And that's one of the things that we mentioned in the prior example. When you're dealing with shell elements, this is not a global X or global Y. It's the shell elements, local X and local Y. And there is a way to define that. Maybe we will or should, I guess, in an upcoming example. But since I'm looking for a stress actually along this direction, the short edge direction. That is about 15,722. It's pretty simple for me to toggle between those two and locate which one it is. So here we can see our results. We have 15,849 at the unconstrained edge. So that is what we are going to utilize to compare to our spreadsheet. There's the flip side of the model. So they're the same results, just one in tension and one in compression. Let's go ahead and plug that result in and see where we are in comparison to our hand calc. 15,849 versus the 15,772 gives us a difference of less than 1%. We're at 0.488%. So great to see. There's another validation showing that the Nastran is giving us some results that we'd expect. So hopefully you enjoyed that example. Thanks for watching. Hope you have a great day. Take care.